Welcome. Today we'll be discussing topics from Chapter 2. This is in preparation for Exam 2. For our first example, we'll start with find all solutions. To sine of x equals square root 3/2. So with sine, since this is between -1 and 1, we know that there is a solution for it. And we know that we'll have to find two solutions because it is not 1 or -1. So first, we'll find that sine inverse of our base angle of square root 3/2, we can look at our unit circle, or through memorization, we can get that this is pi/3. And we'll denote this as x1 or x0. Okay? And x1 is equal to pi minus x0. So we have pi minus pi/3, which is 2 pi/3. These are our two base solutions. To get all solutions, we have to add 2 pi n to each one of these. So our answer looks like the following. All solutions are in the form of x equals pi/3 plus 2 pi n, or x equals 2 pi/3 plus 2 pi n. And that will be our answer. For example 2, we're going to have f of x is equal to -6 sine of 2 pi/3 plus 2x. And we'll want to put this into standard sine form, as well as find the amplitude, the period, and the phase shift. So first, what does it mean to put it into standard sine equation form? We'll have to have a positive coefficient in front of the sine, a positive coefficient in front of the x, and then we can write down the rest of the information. So there's two ways that you could think about it from this point, starting from this point. The first way that you might go is, hey, I can, sine's an odd function, so I can make the inside be negative and the outside will also gain negative, making it positive. But if we were to do that, we would get something like this. We have 6 sine of -2 pi/3 minus 2x. And that doesn't work because now this is negative. We'd have to deal with that. So instead, what we can do is look at our identities and say, hey, there is the add pi identity, which is sine of x is equal to negative sine of x plus pi, meaning that I can times by a negative to the other side, and I get negative sine of x is equal to sine of x plus pi. All right. Well, if we use that, we get f of x is equal to 6 sine of 2x plus 2 pi over 3 plus pi. And we can finally rewrite this as 6 sine of 2x plus 5 pi over 3, giving us an amplitude of 6, a period of pi, and a phase shift of 5 pi over 3 to the left. Now, I write to the left because that is showing that I am moving the entire graph to the left. You could try and write negative 5 pi over 3. However, that's subject to interpretation. It's best to just be descriptive with it. And the amplitude we got because of our coefficient here being 6, and the period we got pi because we'll take 2 pi divided by the coefficient in front of x, which is 2. And so this is the answer we're looking for. Now, because it's sine, we could also do a couple of other things. We might also notice that sine of x is equal to sine of x plus or minus 2 pi. So if I was to subtract 2 pi from this, we would get f of x is equal to 6 sine of 2x minus, and we get pi over 3. I use the x variable. Let me make this theta. Theta can be equal to this entire input there of 2x plus 5 pi over 3. And when I subtract 2 pi from it, I have 5 pi over 3 minus 2 pi. That gives me negative pi over 3. And now this, we could write down the same thing. We get the same amplitude, same period, but our phase shift would be pi over 3 to the right. And that is not a wrong way of thinking about this. If we were to graph it, you'd see that they would align exactly. Just one is shifted to the right, the other shifted to the left. And if we look and see that the total phase shift that we did was 2 pi. So we just kind of picked up the graph and shifted over and dropped it on itself again. So that is second example. For a third example, we can do sine of cosine inverse of 5/13. And we want to find the exact value. So when we first set this up, we can go, okay, what's cosine inverse? Well, that is cosine of some theta equals 5/13. And because I didn't list anything about this, I know that it must be within the first two quadrants here. It's somewhere within there. And if it was negative, it would be somewhere in here. If it was positive, it would be somewhere in here. And so I can just draw the triangle out. So let me draw this triangle of theta, and I get 5, 13. Well, that tells me that I'm in the first quadrant, because if it was a negative here, I'd be in the negative x quadrant. I'd be in quadrant 2. So I know I'm in quadrant 1. So now I have to figure out what this side length is. And we can just do a simple calculation. It's Pythagoras theorem. 13 squared is equal to x squared plus 5 squared. And we have 169 is equal to x squared plus 25. Subtract 25 from each side, and we get 144 is equal to x squared. So x is equal to plus or minus square root 12. Which one are we going to take? Well, we're in the first quadrant, so sign is positive. Therefore, we must have the positive part. I can ignore the negative. Oh, sorry. This is plus or minus 12. That's square root 12. So x is equal to positive 12. Let's put 12 here. Now we take sine of this angle, because that's what cosine inverse got us. We got back this theta. So we're taking sine of theta, well, as opposite over adjacent. So sine of theta is equal to 12 over 13. And there's our exact value. Yep. And for our last example, example 4, we can see this. Cosine squared x, actually no, sorry. I want sine squared x plus 5 cosine x equals 5. We want to find all solutions. So your first guess might be, hey, let's substitute. And we can have a, b, sine. Oh, we have cosine here. So we have to make one of these look like the other. Which one's easier? In my opinion, I take the sine and make it look like cosine, because we have the Pythagorean identity of sine squared x plus cosine squared x equals 1. Well, if I subtract cosine squared to the other side, I get sine squared x equals 1 minus cosine squared x. So I'm going to substitute that in for our sine, getting 1 minus cosine squared x plus 5 cosine x equals 5. Let's bring everything to one side. So when I'm going to have a 0 on the left-hand side, I'm going to subtract 1, and I get 4. I'm going to subtract 5 cosine x, and I'm going to add cosine squared x. Let's make our substitution, having a be equal to cosine of x. And we get 0 is equal to 4 minus 5a plus a squared. We can flip it around to make it look standard. And we can write 0 is equal to a squared minus 5a plus 4. Well, through factoring, we can get 0 equals a minus 4 quantity times a minus 1. So what does this tell us? This tells us that a is equal to 4 or a is equal to 1. Now remember, a is cosine of x. So this is really saying cosine of x is equal to 4 or cosine of x is equal to 1. Cosine of x has a range of -1 to 1, meaning we can never reach a 4 with just cosine. We'd have to have a coefficient of at least 4 or more. So we don't have that. We don't have the correct amplitude. Here, cosine of x does get 1 because it's between -1 and 1, but it's exactly 1. So when we evaluate cosine inverse, x equals, let's do arc cosine of 1, we can check and see that that occurs at 0, and therefore we're going to add 2 pi n to that. So generally when we take our cosine, we get a plus or minus answer, but +0 and -0 is just 0. So we can then just drop 0 all together and go x is equal to 2 pi n. And if you want to include that n is an integer, you very well can. It's implied, but you can include that into your answer and you will not be wrong. Thank you for watching and have a great day.